welcome to another episode of Harrison Hobbies. Today we are going to continue our series on the M18 power converter build. So over the past couple of videos we've gone through and we tested what kind of current that table saw, the M18 table saw, required, and we tried it with just one of our power converters and discovered that that wouldn't work. We then went in and built a second converter and tried powering it, still wouldn't work. Through that experience, we discovered that it wasn't the power converters that were actually having an issue per se. It was that their voltage, whenever the load was getting heavy, their voltage would drop quite a bit to the point where the saw would think that there was something wrong with the battery. So in doing that, we tried using a helper battery to keep the voltage where it needed to be. That worked out fine, but I felt like that was still kind of cheating a little bit. And so we went in and built a bank of capacitors. So these helped keep the voltage normalized, and the saw didn't end up tripping out whenever we were using these. From the results there, we discovered that we were using at least 2,000 watts according to my ammeter. We probably have some capacity still on the table here because from the last test we saw that we were running really under load around 18 volts. And so we know that these tools are built to handle a peak of 20, which would be what a fully charged 18650 battery is. We can probably get a little bit more speed from the blade, so we should be able to increase performance. So what these are going to do is take the 18 volts-ish out of these converters, and it will be able to step it up to 20, I think they go up to 36 volts. I have a high degree of confidence that our tools will not handle 36 volts, but we're going to try to get it dialed in at 18, 19, 20, maybe even push to 21 or 22 volts and see what kind of behavior the tool has. We're going to be kicking off testing with our sacrificial Milwaukee drill, but the way that we're going to quantify this is we have an RPM meter here, and so we'll be able to put that onto the chuck, and then we will hook up one of these in line, and we'll try to get an XY plot where we're going to have probably voltage on the horizontal axis and we'll have RPM on the vertical, and so if we can see if we can find some kind of correlation in the tools. If everything looks like it's going okay, then we'll hook it up with the table saw. So that's the game plan for the actual testing and build part. Before we start the video though, I wanted to make a couple of points. First off, everything that I'm using, I always get tons of comments like, hey, can you link me all this stuff? In every video, I have a link to my Amazon affiliate store. So before we really kick off the video here, one of the things that we discovered in our last video was that the anticipated donor battery wasn't going to work because it had too much of the, I guess, the proper charge circuitry. So what I did was I'd purchased the EPOWON 6 amp hour, well, at least according to the label, and the 2.5 amp hour from both of these EPOWON, or however you want to say that. Whenever we crack these open, we can see that it has the exact same board layout as the batteries that we've been using for our project here. So this is our 6 amp hour. Pull apart. So this is going to be our 6 amp hour battery here. We can see, it's basically the same thing. It's got some capped on tape over the leads here. And then this is our 2.5 amp hour. The boards are identical on these. If we look at the tabs, they are both the exact same thickness, the exact same form factor. Really, your top plane here is going to be the same on both. The only difference is you're going to have a middle carriage here with an additional set of batteries. I will keep the link in the description of this video to these on Amazon, and if you're in need of some 18650s for flashlights or any of your other projects, it's probably a better deal to get your 6 amp hour here. But if you want to go a little bit cheaper, the 5-cell 2.5 amp hour is probably going to be your better bet. But yeah, looking at both of these, they're virtually identical. I wanted to kind of go through here and point some things out. In previous videos here, we've taken our wires and we just kind of stuck them into the terminals. We were very, very close with our AC in, our mains in. Those terminals, the wires were very frayed, and I was constantly worried about electrocution and shorting. Same thing on these. There wasn't the greatest connection on any of these. So what I did was I went in and got some heat shrinks and weatherproofed connectors here. and I staked them all down with the screw terminals. So theoretically, it certainly looks a lot better than it did. It should be a little bit safer. Same thing on here. You know, we used some different sizes as we went through, but the exact same thing. One note, due to the width of the terminal block here and these little, I guess, kind of dividers, the set, and I'll link the set that I purchased on here, but they were a little bit too wide to fit onto these terminal blocks, so what I ended up having to do was use my bench sander, which is right there, and then kind of sand down the edges of these so they would fit in a little bit better. It only had to kiss the very side of it in order to get it to work, but hopefully this will be a little bit less sketchy, a little bit more safe, since that was actually one of my concerns. So the basic game plan here is we have two of these. I think that I may have undersized these. They're supposed to be 1500 watt each. However, they're potentially, I think it's 1500 watts if you have like a 60 volt in. And since we're only going to have 18 volt in, we are probably going to need to have 4 of these all splayed out. So the game plan here will be, we're going to create some more squids with the XT60 connectors feeding in. Every one of these is going to have 2 positives and 2 negatives. And then we also have our output here. We're going to be using our bench power supply here, very small, and we'll try to get some voltage readings over here with the multimeter. So just so we can see, I have this bench power supply here. Specifically, it is dialed into about 19 volts, which was what these power converters can actually handle. And we have our inverter here. We have our multimeter leads hooked up to the multimeter here, positive and negative. And this potentiometer here is the one that we are adjusting. It's right next to the leads right here. So right now we have this dialed down to 18 volts, 18.2. So we're going to keep turning this a little, and I mean, this is a couple of degrees per, fraction of a volt, and we're going to get this dialed into, let's say, 20. As a sanity check here, let's do a quick voltage test on a fully charged M18 battery, and so we're seeing about 20.4 volts. So that's with our battery here. It's a very, very sensitive potentiometer. Close enough. Okay, so this one should be ready. We're going to do the same thing on the second one here. There we go. Okay. And now that's going to start up here at 46, so we're going to do the same step down here. Now it's good to spin it a whole bunch and then stop after a couple of rotations because the voltage will continue to fall, likely as the capacitors bleed off their charge. Okay, I think that's about the same. So the game plan tonight is we have more of these little heat shrink connectors here. So none of them really fit onto the terminal blocks that well. So what we're going to do is take the center hole on all of these, which you probably can't see, but it's right there in the middle. We're going to drill these out a little bit so they'll fit into the screw terminals. We have some 22 to 16 gauge, and we have a whole bunch of 12 to 10 gauge ones. What we'll do is we will build ourselves some squids. So we're going to take our, on one power supply, for example, the XT60 and 90 will be the same format, but we're going to take our female XT90, we're going to have a male XT60, which would normally plug in. What we'll do is we'll have 4 wires coming out of this negative, and then another 4 wires out of the positive. On all of these, we will have these little connectors here hooked up, and then on the output here we're going to take the more of these stakes, hook them up, and then on the other side we're going to have a female XT60 connector there, and so that will come out, and so basically this will just be an inline converter, and then we have the opportunity to plug both of these into a squid. Again, I am not an electrical engineer, so if anyone here is or is better versed in electronics than I am, let me know if what I'm doing is wrong or potentially detrimental. This may save tools in the long run. I guess now the thing to do is probably just cut over to some time lapse. So a bit of a reconnection here. About 2 months ago, I started working on this, right, early January. I believe my plan was originally to have both power supplies feeding both of the inverters. However, I guess in hindsight now, instead of that, my intention is now to keep these as two discrete systems, and so we're not combining this. Boost converters are actually only 1,000 watts. So, to compensate for that, I decided it may behoove us to add on an extra 2,000 watts. So now we'll have 4,000 watts total. We can put the capacitor bank in, we can have batteries, we can have everything, and we would be able to step up our voltage coming out of anything. So now a 20 volt battery or 22 volt, whatever, isn't actually going to be 22. We can push that up to 24, 25 volt. So we're going to end up with all four of these in parallel. And then coming off of these, we're going to end up with, this is not the right format for the battery. We'll end up with, what, 2, 4, 6, 8 positive and 8 negative leads into a single XT90 connector. So, yeah, so this is what it's going to be here. I think that's going to work. Now, as I sit here with this physically in front of me, I'm starting to get my own doubts, but we'll keep the fire extinguisher handy on this. So what this should give us here now is going to be four positive and 4 negative outputs. So we're going to have our squid here, and we have, for example, one of our power supplies plugged into the squid. Now this is going to give us an output here, and we're going to be able to connect this output here. So that'll give us a positive and negative set of wires for every one of our boost converters that are right here, all 4 of them. And once this is done here, the next step will be taking all of our positive outputs and then having a 2-to-1, 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 and then that 2-to-1, 2-to-1. And so we'll step down until we're at a single positive and negative leg, and then that will ultimately connect to our battery. So now we're starting to get our wires here. I guess our game plan now is going to be take our 4 XT60 connectors here and solder in 8 pieces of wire into those 4, and then we will stake on our orange, or not orange, yellow crimps. A little while ago I'd misspoken. I'd said that this was the input here. I was actually mistaken, and this is going to be our input side. We have a positive, or a negative here and a negative here, and so this entire brighter chunk of the pad is actually all a trace underneath, and then there's an exposed trace that's going to this leg here of the MOSFET. And same thing here. the entire pad's going here, and then we end up, these are all the fuses on one side here, and then looking through here, fuses. Okay, sorry, this is, okay, they've got 2 stakes, so these are all of the fuses here. So this is all, this leg here double crimped. So these are all the positive of the fuse, and then, or one leg of the fuse, and then this is the other leg here. So they're separated by the trace. So a little bit of a panic attack there, but my assumption is correct that we've increased the sketchy factor by only using one of each terminal leg, but there really isn't an issue in doing that. Based on what I'm seeing here, though, I'm probably going to swap the negative over to this one, since this one is directly plugged into that trace, so we may see a little less resistance. So I got that put back together, and we have the wire installed here. I am going to go do the same thing for the remaining 3. So continuing our game plan, I've got legs added to all of these now so they can freestand. They're not going to be sitting on the fan. They're going to be a little bit more stable. At this point, with how much I've mixed and matched the wires based on what's been easy to assemble, there is absolutely no reason that I need to have, I need to maintain size anymore. But just to kind of keep things a little bit more pure, we'll use XT60s there. I guess we will restart the time lapse here again and get these soldered up. Welcome back. I believe we are on day 3 of recording now. We've got our power supplies here, 2 of these. We have our squid here to accept 2 power supplies of input, plus batteries, plus capacitor bank, plus anything else we want, and that's going to give us 1 output. We take that 1 output and we splay this back in to 4 outputs. So now every one of our boost converters here can get their own input. The advantage of having all of the inputs upstream of these instead of downstream is that whatever voltage, or I guess current sources we apply here, can have the same step up. So now the next step here is going to be to pull out a multimeter, and we are going to get the nominal voltage of every one of these step up transformers here about the same, and then we will combine them all, check out the sine wave, make sure that there's nothing funky going on, and then assuming that works, we will then take our donor drill here and we will do a quick voltage to RPM correlation, right? So we'll plot that XY. Then we will go get the table saw and we will hook that up, making sure, again, we're at a safe operating voltage here, and then we will confirm that everything is as it should be. So our first step is going to be to see what voltage we have coming out of our power supply, and we have 18.8, right? So we are roughly 2 volts lower than we'd like to be. So now we will plug in our inverter, or our boost, and we can see a red light here indicating that this thing does in fact have power. So that is good. We're going to check our positive, and we're running 20.47. let us modify the voltage here just a tiny bit. There we go, 20.52. So now we're going to be working closer to a fully charged battery here. So now let's look at what our sine wave looks like. And let's see if this is going to be easy enough to do. So we got our oscilloscope now that we'll hook in. There we go. Okay, so we're seeing here that it's complete. I guess that would be why I'm like, where's the sine wave? No, there's no sine wave. It's a boost converter. So we now have this good. We're seeing that it's a flat line. Again, this is not a professional oscilloscope, right? And it is not going to pick up a lot of the nuances of any kind of waveform. But it's going to be enough that we can tell this isn't spiky or jagged or really discontinuous. So we'll get a couple more of these done, and then we'll do the exact same thing and see what the resultant output is. Might as well just get them all plugged in at once. So now let's add another one of these and validate that we're good. We got negative and positive. Okay. Ooh. Ooh, that sounds more powerful. And we've got all three of these now. Okay. Everything here seems to be working pretty well. So I guess our next task is going to be to correlate RPM with voltage. So because I don't want to have to worry about adjusting voltage on all of these, actually, let's time out there. Let's look at what our sine wave looks like too. So because all of these are electrically coupled, I guess I can hook up to any of these theoretically and I will get the same result. So we will hook on to maybe this one. There we go. And let's hook on to the screw head. Okay, so we have the plus 19.1 and the minus. And it is a nice flat wave. I would argue that I see less jitter here than I did with the other one. So it may be that we actually, there was probably a little tiny bit of chop here that was almost indistinguishable because we have all four of these now operating in parallel, that our waveform may have actually cleaned up and become even more uniform. Not sure on that necessarily, but yeah, so let's hook up the drill and start going that way. So our next step now is going to be to plot. Instead of doing this digitally, I'm just going to be taking some hand measurements here. But what we're going to do, if you've never used a tachometer before, we're using an optical tach. And so you can get these on Amazon for super cheap. And effectively what it is going to be a little, basically it's a photo eye. So it's going to emit a laser, and then you're going to use one of these. This is like a 3M reflective layer, similar like at night to what you'd see reflecting on a road sign or a day glow vest or something. And so we're going to put that on our chuck here. We're going to allow it to spin. And every time that this shines the light and this piece instantaneously reflects that back into the machine, it's going to calculate how many times that happens per second, and then that's your RPM, or I guess how many this happens per minute, whatever your unit is that you want. So what we're going to do is kind of pitter-patter back and forth. We're going to probably try to get down to as low as this thing will go, and then up to, I don't know, when we start smelling smoke, I guess. And then we're going to look at what we've got from a RPM perspective. So it's just an adhesive-backed sticker, and we will put that here on our chuck just indiscriminately, just like such. So now when this goes, we'll make sure that we tighten that chuck all the way. So now as we turn, we'll see that. And then I don't think there's going to be a good way to get the camera here. So I'll just read this out, and then once we're done here, we'll put a graph up. Just so you can kind of see, it gives us a red beam there. And so what that's going to do is it's going to shine here. I'm going to read out the results, I guess, just as kind of a demo in case you've never seen one of these in operation. So we got our tape. You can see that. And then now we'll just point this here. And you can see here that we are running, there we go. We're running 371 RPM, 200, whatever. And as we go faster, there's a tiny bit of a latency. So here we're capping out at around 1600, 18. So the reason that we saw a whole bunch of fluctuation there up to 2000 or so RPM was because if we were to put two of those pieces on, for example, you'd get double the reading. And so on here, there's probably some grout and stuff left over. It's, you know, glossy metal. And so there's going to be some false reflections there that this will take into account. When you get into higher end ones, you know, not the $20 one, but once you're talking, you know, hundreds or thousands of dollars for one of these, they start getting a lot better at being able to filter that. And they're looking for specific wavelengths, not just pure reflection. So I'm going to do that from the comfort of my chair, and we're going to get a curve that was running. Let me put these back into our squid here. Okay, so 20.49, and we'll just have a list here, 20.49, and then we'll hit voltage here again. So I'm seeing about 1625. And I figure we'll probably try to take our voltage and then go up half a volt, down half a volt, and we should be able to get a pretty good line. Just a quick recap of what we saw from the testing here. We went from around 18.5 volts up to around 22 volts. I didn't excel beyond 22 volts because we saw a pretty linear trend here, and I figured it wasn't worth damaging my tools here to figure out what the upper end was going to be. But the major takeaways from this are for every half a volt, we're gaining roughly 50 RPM. So that would mean that every volt we have is going to be at 100 RPM change. So if we were to go up to 22.5, we're going to be probably running 1750. And above that, you know, we're going to be doing a step function, like I'd mentioned, of around 100 RPM for every volt that we add. The last step is going to be the moment of truth. If this works, then I feel like this project's going to be wrapped up. The only thing I'll have left to do is bring out my label maker and label all of these, which should be a good time. But yeah, so what we'll do is we'll hook up all these in parallel, and we will then plug them into the table saw, and we're going to see if we can still make a cut. Bearing in mind that we still have accessories such as our capacitor bank to help with starting. We've got a lot of things, and the beauty of the way this is set up is anything that is upstream of these, their voltage doesn't really matter, because these are going to take any voltage that they're getting, and they're all going to uniformly be putting it out as whatever voltage we tell them to. As low as, what, 18.71, and as high as what we saw whenever these kicked on, 50 volts. These have such a range here that, and you know, if we would have spent more money, we probably could have gotten a 12 volt version of these, right? And so now if we were to build multiple battery packs, right, you have one set of inverters or converters, and you have, you know, your XT90 connector here, and you have a M12, you have the DeWalt 12 volt, you have the DeWalt 20 volt, you have Milwaukee 18 volt, Makita, whatever. And so you can have a whole range of batteries and voltages that all work with this. So it's certainly an interesting concept that I think will be fun to play out in the coming months/years. So without further ado, let's put this to the true test. This project has been a long time coming. I think using one power supply seemed easy enough, right? I wasn't too afraid. Hooking up two, I was a tiny bit concerned. Having this entire setup here, this is the first time that I've actually been nervous for one of these videos. Moment of truth. Let's hook up a helper battery in case that's what's causing this. We now have these fancy adapters here too. In addition to this one test, I did the test several more times, but for whatever reason, the video isn't around anymore. But what I had observed there was, first off, you could remove that helper battery from the circuit, and the saw would continue just fine. We were seeing a similar voltage sag of around 17 volts. But the way that I'd figured out to get the system started was to take that helper capacitor bank and then put that downstream of our boost converters. And so basically the saw could draw directly from those instead of requiring the boost conversion and then receiving the power. So that worked out pretty well. However, in every test, we were always seeing the voltage drop down to mid-17s. So that's leading me to believe that the boost converters aren't actually able to keep up with the system, and it's taking the native voltage from the power supplies. So I think the next step here is going to be to remove any kind of boost conversion there and instead get some 24-volt power supplies and make sure that we can get those dialed down to around 22 volts so we're in a more safe operating range. And in addition to that, I think that we're going to need to look into larger capacitor banks to be able to help with more of that sustained load and being able to smooth out the peaks and the valleys. So for starters, in previous videos, there was always a tiny bit of reluctance, probably isn't the right word, but the saw didn't necessarily have, it didn't feel like it had as much power as if it were running the M18 battery, like one of the bigger ones. This right here, I wasn't going super hard on that board, but like in day-to-day, that's probably about as far as I would have pushed it, right? Like that felt comfortable. I would say that it is on par in terms of that cutting performance with what a brand new, freshly charged 9 amp hour battery would do. A lot of people have reached out to me regarding me making and selling these. To get the wiring done, to get all of this done, I'm not an electrical engineer. I'm a mechanical engineer by trade. I design warehouses and distribution for my job. So this is not my wheelhouse. I am not fast at this. I would say that a lot of this probably isn't necessarily done right. I will not make and sell these devices. These tutorials are here for you to try it yourselves, and I'm here. I try to respond quickly to comments if they're asking any questions about the specifics of this. Happy to walk anyone through. But I'm probably, realistically, I'm 50 or 60 hours into research, design, build, test of these here. Granted, if I were to build one of these again, it would probably be faster, but I'm still looking at, a full, solid, good chunk of a week to build one of these. That being said, somebody a while back had mentioned a Kickstarter for these. If you would purchase one of these, please comment and tell me what you think it would be worth, right? I mean, right now we're looking at 100, probably, in parts alone, and granted, these are not bulk discount or anything, these are just from Amazon commoditized. But including cable and all of this, I'm looking at probably $400, maybe even $500, possibly $600 in gear to make one of these. So, granted, you get into economies of scale, that price comes way down. But I'm wondering for home gamers, for tradesmen, tradeswomen, trade people, what would this be worth to you? And if we can hit a price point that I think that we could probably make these at, it may be worth partnering with some electrical engineers and some manufacturers to see if we could actually make this real. Further to that point, I guess open call here. If you're an electrical engineer, you've got feedback on how to do this, you think that you could quickly create, the circuit schematic so it's not as modular and as splayed out here, and you'd be interested in helping with this project, I'd be interested in talking to you as well. So feel free to shoot me a message or comment, and we may be able to turn this into more than just a bunch of videos, but actually, a product line here if these tool manufacturers aren't willing to step in and start building these. So I guess in close here, I feel like we've probably wrapped up the design and build chapter of this. This is hack job engineering. This is nothing to do with the tool build. But I think, again, this channel is kind of about learning. It's about trying things. It's about the stuff I would do in my free time. And I just do it with the camera on. So anyway, next steps for this is probably going to be, as I'd said, get these labeled so it can be rebuilt and reproduced by other folks, and get this boxed up and hopefully send it off to Torque Test Channel, assuming they still want to test it, and see what kind of performance we can get, and then see what we can do if, you know, if there is interest in commercialization, trying to get some of these produced. And if you have any ideas on how this could have been done better, let me know. I'd be happy to hear that as well. With that being said, thanks for watching, and check back soon for more videos.